So, welcome everybody to our second external research seminar. We are Neural Magic, and we level the machine learning playing field by turning everyday CPUs into high-performance machine learning compute resources. We are pushing the envelope when it comes to the model compression research, and thus we also regularly host research seminars under a moniker Lunch and Learn. And why Lunch and Learn? Because those take place during the lunchtime in Boston, and we also, learn something new. So this is why Lunch and Learn. Today, I also hope that you will learn something interesting and new. My name is Damien. I go by the name of DTransposed on socials. And speaking of socials, I encourage you to follow us on Twitter, join our community on Slack, and give us stars on GitHub. We have big plans for this year, so I can promise, follow us, it will be worth it. And now, just to go through the agenda for today. So first, I'll talk about, let's say, the background required. So it's about pruning, model compression, and sparse training. Then I'll talk about ACDC framework. So I'll just walk you through the algorithm and share some of the key insights. And finally, I'll share results for the computer vision domain, for NLP domain, and some of the inference speedups, which we are very interested in Neural Magic. And finally, there will be time for discussion and Q&A. All right. So let's start with the background on pruning and sparse training. For this presentation, I'm just assuming a rudimentary knowledge of machine learning and deep learning. So if you know what backpropagation is, convolution is, what multi-layer perception is, this will be sufficient. And I will just try to introduce new concepts on a fairly high level. So first, model compression. So model compression is the process of reducing the size of a neural network while maintaining its accuracy. There are several techniques for model compression. The three most important ones, I would say, are knowledge distillation, quantization, and pruning. So knowledge distillation is basically a process of where the larger, more complex network is used to train a smaller one. The smaller one is trained to predict the output of the larger one rather than the ground truth labels. And this process distills the knowledge from the larger network to the smaller one, resulting in a more compact model with similar accuracy. Quantization, on the other hand, is the process of reducing the precision of weights and activations in a network. Most networks use 32-bit floating point numbers to represent weights and activations, but reducing the precision to 16-bit or 8-bit integers can significantly reduce the memory and computation requirements of the model. And finally, the most important method for today is pruning. Pruning is basically a process of removing the unnecessary parameters from the training. So very often, after we are done with training, many of the parameters are actually redundant, unnecessary, and do not have a big impact on the quality of the model. Right? So basically, the goal of pruning is to maintain accuracy of the network while decreasing its computational cost, for example, during inference. And in the context of pruning, we very often talk about two representations of the same architecture. Dense representation, which is the network as we know them with full unpruned weight matrices. And there is also a dense representation where some of the neuronal connections are being removed as compared to the baseline. And another point is that in general, we can divide pruning methods into categories. We have unstructured pruning, where individual parameters, for example, individual weights in the weight matrix, are removed. For example, we remove 50% of the smallest weights in terms of magnitude. And those removed weights, right, they can be scattered throughout the network, wherever. So this is why we say that the sparsity is unstructured. This approach can lead to reduction in the number of parameters, But as of today, the most popular commodity hardware, such as NVIDIA GPUs, have difficulty utilizing the full potential of this method. And this is actually where we as Neural Magic step in. We have very good understanding of the problem, and we have, I would dare to say, harnessed this unstructured pruning to deliver great benefits for the users, for example, in terms of the inference time. And there is also structured pruning, which on the other hand is more targeted approach to pruning. In structured pruning, the entire rows or columns of weight matrices are removed rather than individual parameters. So this creates the structured sparsity pattern in weight matrices, which is more widely supported on the commodity hardware. So just to make you aware of how powerful pruning can be in practice, I would like to show you some of the data which comes from our from Sparse. This is our model repository for highly sparse and sparse quantized models. So if you go to sparse.neuralmagic.com, you can take a look at those models, you can download them, you can play with them. But my point is here that let's take a look at the Resonant 50 models. I've highlighted the two versions of it, the dense representation, which is the base one. So as you can see, the accuracy of this model is 76%. The speed is about 300 items per second, and the size is roughly 100 megabytes. Now, our pruned version, which is 95% pruned, so this means that 5% of the weights are kept, right? So effectively, we go from, I think Resonant 50 is about 60 million parameters, so we go from 60 million to about 1 million, roughly. So we prune this model. And even though we have removed so many parameters, our accuracy drops by a fraction of a percentage point. Our speed increases by a factor of 3, roughly, and our size decreases almost by an order of magnitude, which is pretty significant. Same thing with BERT, so the model from NLP domain. Pruning BERT, as you can see, also does not impact. It has a negligible impact on its accuracy, while you can enjoy the increase in speed of roughly 4x, and the reduction of size of 50%, right? So my point is here that pruning can be a really powerful method for deploying more efficient models. And now we've gone through pruning, which has been a good introduction to sparse training. So most of the time, where you think about pruning, it's being done in the framework called post-training pruning. So what you do here is you basically train the network as you normally would, right, in a dense way, and then once you obtain a optimized dense representation, you will take a look at the weights and just remove the ones which are least impactful. The problem is that you basically you have to train in the dense way. You have to get this dense representation. So you have this like a intermediate representation, which we can maybe be a bit smarter about this. So what you can do, you could do sparse training, which means that you remove as many weights as possible, not after training, but before training or during training, as many as needed to reduce the computational cost of training, but not too many to ensure that the quality of the network, the final network, sparse one, is preserved as much as possible. The benefits of sparse training. First of all, you do the forward pass and backward pass only over a sparse support, right? So you don't use all the parameters of the dense network, but you only use a subset for forward and backward pass, which essentially reduces the computational cost. With post-training pruning, so that this other framework which I described, you only get the inference the computational savings at the inference time, right? Because you train in a dense way. With sparse training, you basically enjoy the computational savings both at inference and also while training. Also, sparsity is in general known to be a good regularizer because it encourages the model to have fewer non-zero weights, which helps to reduce overfitting, by reducing the complexity of the model. And finally, as I said, if your end goal is to have a sparse model, why would you go through this, intermediate phase of getting a dense model? Why just like the smart idea is just to go directly at the target. So go just get the sparse representation directly. All right. So why does sparse training matter? Well, it is well known that the performance of networks, deep neural networks, scales as the power law with respect to the model capacity and training data. So to get a noteworthy improvement on the problem, so to reduce the error by a small margin, you need a massive amount of new data or additional compute. How sparse training can help here? Well, first of all, because we have less weights here, we can basically lower our memory requirements during training, so our peak memory usage decreases. We also use lower per iteration computational flops. But this does not always mean that we use less total training flops, right? Because sometimes those sparse training algorithms could take significantly more iterations and epochs to converge. Luckily for ACDC, which I'll introduce in a second, this is not the case. So ACDC also in general reduces the total number of training flops. And sparse training is still there is still very active research on sparse training. There is one more paper which has been released right now, also by the authors of the ACDC, which is about the sparse prop, so backpropagation on the sparse weights, which is also not a trivial problem right now. And you can see here that just a small point here. The authors show here that you can maintain roughly the same accuracy for different data sets, while your backprop takes 5 times less time. So my point is here that sparse training is really useful, and there is still active research on how to make it even more useful. All right, so this is the necessary background, and right now I want to dive into the framework itself. So ACDC, alternating compressed decompressed training of deep neural networks. It's a joint research by IST Austria and Neural Magic. So let me just step by step walk you through the whole algorithm, right? So first of all, let's just take a ResNet and let's just train it on ImageNet. And we're going to begin in a very standard way. So for the first 10 epochs, we're going to do like a warm-up training. So we just train in a dense fashion, right? And this is just to establish a good set of initial dense weights. After epoch 10, we enter the so-called compression phase or sparse phase, where we say, okay, now I want to spend 5 epochs sparse training. So I take a look at all my weight matrices globally in the whole network. So right now, imagine that this matrix, the small matrix, represents all the matrices in your network, at least the most important ones, like convolutions, for example. So we take a look at those weights, and we say, let me take a look at top K most important weights in terms of magnitude. And here, I choose K to be 4, right? So I keep 7, 6, 7, and 9. And then I zero out all the remaining weights, right? I have this sparse support, the sparse weight matrix. And then what I can do is for the next 5 epochs, I can train. And I'm going to, sparse training is not a trivial problem. And this paper also has a contribution in this field. But right now, assume that, this is a black box. You know how to sparse train. So you basically, you get some more optimal weights after those 5 epochs. And then you want to enter the dense phase once again, right? So what you do here is you just reintroduce the weights from the beginning of the sparse phase, right? So you just basically copy and paste them into the missing fields, I would say. And then, you have your new dense weight matrix, and you just continue training in the dense way for next 5 epochs. And this is why we call this ACDC, right? Because you basically alternate between sparse phases and dense phases. Sparse phases are there basically to approach the best sparse solution, and dense phases allow us to explore the whole set of solutions, right? At some point, right here at the epoch 90, you make a decision. You either continue training in the dense way, and you get you basically you get an optimal, sorry, not optimal, but you hit like a local maximum on the weights of a dense model, right? So you finish training of the dense model, or you can continue training in the sparse fashion, and then you're going to get the optimized sparse representation, right? So this one training run can actually give you 2 representations, dense and sparse. And that's the pseudocode for the framework. It basically just I can just like reiterate what I have told you before, right? So in the nutshell, we have weight theta, we have some data, we have sparsity k, which is very often just expressed as the percentage of the weights that we want to remove. Compression phases, which are the indices of the epochs, and also decompression phases, which are also indices of the epoch. We iterate over epochs in line 2. In line 3 or line 7, we basically decide whether we want to enter the compression phase, choose the top K weights, and apply the mask. It's going to only keep those top K weights and zero out all the remaining weights. Or in the decompression phase, you basically you pass through all the weights. And then once you apply the mask, you get the support for the gradients, and you just optimize over the active weights. Right? So basically, same stuff as I just described in my step-by-step presentation. All right, so the key insights of ACDC. First of all, as I mentioned, sparse training is not trivial. The authors of ACDC basically piggyback of the algorithm, which is called IHD, iterative hard thresholding, which basically performs a projected gradient descent on the set of sparse solutions. But the problem is that IHD works only in batches, right? So the authors of ACDC propose a stochastic IHD. On the high level, you can think about it, stochastic IHD is to IHD what stochastic gradient descent is to gradient descent, right? And this has a nice property that under some analytic assumption, this algorithm we ensure the convergence of this algorithm. Another key insight is that, as I mentioned, we can basically get both sparse and dense representation, all at the cost, computational cost below that of a single dense run, right? Because we have this alternating sparse dense procedure, right? So it's pretty cool. We not only have a not shorter but less computationally demanding training, but we also get those 2 representations for free, I might say. Also, the authors show that sparse training using ACDC outperforms the post-training pruning, right? So this method when you first dense train and then prune after your network converges to a solution. It outperforms the aforementioned method both on the sample agreement between dense and sparse representation, right? So those 2 representations, they will not entirely agree always because they're a bit different, but we want to make them, as agreeable with each other as possible. And also, ACDC is superior when it comes to the accuracy, especially for high pruning values. And by high, I mean 90%, 95%, 98% pruning. And finally, it reduces total training flops. From experiments, I can say that it roughly halves the number of training flops. Okay, so those are the key insights. And right now, just to put my money where my mouth is, I'm gonna show you the experiments. So first of all, we're gonna take a look at the computer vision field. Here we train Resident 50 on ImageNet. As you can see from the diagram on the right-hand side, first we have this warm-up period where our validation goes up very quickly, and then we alternate between the sparse and dense training, where in the sparse training our accuracy goes down a bit, and then it goes up, down, up. But in general, we have a nice validation curve, which seems at the end to basically converge to a nice local maximum. And when it comes to the table on the left-hand side, it's basically ACDC compared to other state-of-the-art methods. But what I want to highlight here is how ACDC compares to the dense baseline, right? So we have a dense baseline on the top, and then two ACDC runs. One which removes 95% of the weights, and the other one which removes 98% of the weights. And the main takeaways here are, first of all, the sparse training, the pruning basically only degrades our accuracy by few percentage points, which is not bad given that we reduce the number of gigaflops for inference by roughly an order of magnitude or even 2 orders of magnitude in case of 98% pruning. And also when it comes to the exaflops for training, as I mentioned, we roughly half the number, which I think that given the speed up which ACD gives us, this slight decrease in accuracy is absolutely justifiable. All right, and there were also experiments done in the NLP domain, and here we basically also show that for the transformer XL, when we compared the ACDC pruned at 90%, our perplexity only goes up by a couple of percentage points, which is once again very much agreeable. Okay, and now when it comes to the inference speedups, so one important thing is to mention that when it comes to training, right, the NVIDIA's GPUs in general do not support unstructured pruning. So to train ACDC, so to apply ACDC on NVIDIA GPUs, you have to basically reformulate the problem into a structured pruning problem, or you need to use appropriate hardware for unstructured pruning, such as graph core IPUs. But for inference, however, you can use either Onyx runtime or to really benefit from sparsity and speed up. Recommend you to use Neural Magic's deep sparse runtime, and it's actually what we have been testing the ACDC on at the inference. So what you can see here, there are two columns. The first one shows us the real-time inference, which just means batch of 1, and the second column is batch 64 inference. And now we can see that in general, when it comes to the speedups, we see much more speedups at the batch 64, not only because we use more cores, but there is also more potential for parallelization. So the first takeaway is that more and more pruning gives us very significant speedups when it comes to the inference on the CPU. And in general, inference in the deep sparse gives us faster numbers than the ones on the Onyx runtime. But the main point here actually is the fact that for the inference on batch number 1, we just need few milliseconds, right? For the batch inference on 64, we need like a couple of dozens of milliseconds, which for many applications, and especially in constrained environments, it's enough, So it very often makes more sense just to use your, pretty low cost CPUs rather than, purchasing and setting up the GPU clusters. I would say this is, the main point. And yeah, I would like to conclude my presentation here. And I'm open for, any questions and discussion if there are any pending. Thank you so much.
Yeah, Damien, we've been going a lot of questions coming in, so it's been great, and I've been going through a few. The ones that are still pending is one from Paul. Is the sparsity ratio a fixed training hyperparameter for ACDC?
Yes. So for ACDC, right now it's a fixed parameter. So you at the beginning of the training, you have to specify, I will be at every sparse phase, I'll be pruning at the level of 90%, 95, 70%. Yeah, it's fixed for the whole run.
And then another one from Archie. How better in terms of accuracy it performs better than distillation process, assuming sparse network has lesser parameters than distilled model. So I think overall just asking, how does it compare to distillation processes?
This is a very good question. I personally have not worked a lot with distillation. Mark, do you have some more experience on that?
Yeah, I would say that, in terms of distillation, I wouldn't really put them as a comparison for ACDC versus distillation. And this is because, especially when we get into the NLP domain, nearly all of the research that we do on pruning NLP models involves distillation. So as we're pruning these models and compressing them, just the fact of adding output distillation increases the sparsity that we can get to while maintaining 99% recovery by a significant amount. We essentially go from 60% to 90 or 95%. So I wouldn't necessarily compare them in terms of accuracy. They kind of add on their regularization effects and enable higher compression ratios, at least on NLP. CV, we've been doing active research on it, and we haven't yet seen any benefits from distillation, but there are more pathways that we're trying currently to see if we can include those.
I would also highlight the fact that those compression methods, they're not exclusive. You can do you could potentially join them together, use them at the same time, just to benefit from both of them at the same time, if it makes sense.
Great. And then additionally, we have a question on, can we get any speedups with deep sparse on GPU, or is it limited to CPU?
I think that, our philosophy here in NeuroMagic is that we really want to enable people, everyone, to perform inference and in general, use CPUs, because we think that CPUs in general can deliver speedups which are comparable to GPUs, and at least right now, when it comes to inference, we are very big proponents of this idea that CPUs are sufficient, and this is why we focus on CPUs and not really on GPUs when it comes to the deep sparse engine.
Thanks, Damien. And then we have another one from Isaac. How and why is it better than taking a dense model plus compress versus ACDC model plus compress in terms of just inference?
Can you just repeat those two alternatives? So the first one is?
Taking a dense model plus compressing, and then comparing to ACDC model plus compressing.
Okay, I'll assume that compressing here means pruning, right? So I would just say once again that basically in the first scenario, there are, I would say, two, ACDC is better. So the second scenario is better in two ways. And the first way is we bypass the creation of a dense model, right? Which, if you want to get a sparse model, why would you go through the creation of dense model if you don't require a dense model? So here we basically go directly for the sparse model. And also, as I mentioned previously, actually, in the paper, you can see that ACDC, pruning with ACDC, the sparse training, actually gives you better results in terms of accuracy and in terms of the sample agreement, right? So it's something which I just want to repeat once again.
Yeah. And then another one that kind of feeds off of this is why is the ResNet 95% pruning with ACDC giving lower accuracy than your previous 95% results?
ResNet with 95%. Come again, Mark, sorry?
Yeah, ResNet with 95% pruning with ACDC, giving lower accuracy than our previous 95% results.
Oh, the ones which I presented initially. This is not comparison of like of apples to pears. The numbers from Sparse Zoo, they may not necessarily have come from ACDC, I would say, because we have I would say a plethora right now in our toolbox methods for pruning. So this may have been just something else. Maybe something.
Yeah, and I can expand on that a little bit more, Damien, which is that it's a result of us having a lot, just iterating past what's the original ACDC paper. So there's been further improvements on ACDC as well as other algorithms, and actually we will be coming out with an ACDC version 2 in the next couple months, which even further improves on these results. So yeah, stay tuned for that. Definitely sign up for our newsletter, and we'll be able to get that information over to you guys.
Oh, wow.
All right, and then we have, will there be any vision transformer support in the future plan? And I can run through that one as well, Damien. So there is a research paper that we have coming out as well on vision transformers, and so we don't have any productized support currently planned in right now, at least in the short term. But there is research papers that will be coming out on vision transformers very shortly. All right, and then we have a plug for they can't wait when it will become available for ARM CPUs, Android, iOS, and Raspberry Pis. One more thing on this is that we are actively working on ARM right now. We'll be going out with an alpha shortly for servers. And yeah, again, sign up for a newsletter or Slack, and you'll be the first ones to be able to try that out.
Yeah, ARM is coming very soon.
And then let's see, we have, can we use ACDC in Whisper or Wave the Vec models in the case of ASR? If yes, how to use that?
This is hard for me to answer. We're definitely looking at Whisperer as neural magic, I would say. It's going to be difficult for me to tell you whether ACDC is going to work for a Whisperer, just like off the shelf. But definitely, we are looking at the compression of Whisperer. So maybe not ACDC, but we're as neural magic. We probably will have something for Whisperer in the future, right, Mark?
Yeah, definitely. Yeah, definitely. And also, if this is research that you'd like to try out, definitely check out our SparseML repository, because that has ACDC implemented in it, as well as all the other pruning algorithms, and makes it really easy to be able to plug into training infrastructure and training pipelines and pretty much anything else. So if you'd like to try it out, go for it. It should be pretty easy to set up and use. And feel free to ask any questions in Slack or for any problems you run into.
Yeah, I would say, it would be great. And we are there on Slack for you guys if you have any questions or problems. Hopefully not.
And then we have another question for, has this been run on Intel Xeon Phi? And a question on if it has been CPU-like or GPU-like. And let me just pulling up that one. I don't believe we've run anything on the Xeon Phis yet. But yeah, that would be CPU-like. It should, yeah, it would work out fine, but I don't know of any results that we have on that currently.
So training was done just to finish. So training was done on the GraphCore IPU as well as in PyTorch. But like we with PyTorch, we did not get the flops, basically, the speed ups in terms of flops, and the inference was on CPU, I think, only in the paper, or maybe there was maybe NVIDIA GPU inference also with structured sparsity. Yeah.
Let's see. And then another one is unstructured.
So.
All right, sorry everyone, had a spam call come in and try and take over my headphones. So in unstructured pruning, how does flop reduction translate to inference latency reduction?
Well, I think this is the secret sauce of neural magic, right? So we in our DSparse engine, we utilize the unstructured pruning to be able to run inference much faster, right? So unstructured pruning is a type of sparsity, which in turn allows us internally in our engine to run inference faster. So it contributes a lot in our case.
Yeah. And then in terms of the relationship between the flops and the inference, generally it scales similarly, which is as sparsity increases, we're going to see a exponential relationship for speed up, right? So as you go from 80 to 90%, that's the same as going from 90 to 95% in terms of inference speed up. And then we have, as I know, FPGA accelerators are more suitable for sparse computations with integers for inference. Is it possible to adapt ACDC to such hardware platforms?
I don't know much about FPGAs, but I don't see a reason why. What are the constraints of FPGAs? I'm not aware.
Yeah. So towards that, it's definitely possible to adapt to run on those. We've talked with Moffat AI in the past, who actually have used models straight off of Sparse in their infrastructure or in their chip to be able to get significant speed ups. So definitely possible to use those. The models we're generating and the algorithms that we use for FPGAs. And then we have how ACDC helps with regards to using pre-trained network. Does it mask neurons in the pre-trained network or just the top classification regression heads, which are modified?
Can you repeat the question, Mark? Sorry.
Yeah. How does ACDC help with regards to using pre-trained network? Does it mask neurons in the pre-trained network or just the top classification regression heads, which are modified?
I mean, once again, this is something which was not explored in the paper, but it's something which you could very easily implement yourself and test. Because in our implementation of ACDC in SparseML, you can basically choose which layers you want to target. I'm not sure. I mean, definitely should be possible to use ACDC to take a pre-trained network as your initial network and perform some kind of like a sparse fine-tuning. But I'm not sure how it would turn out. Probably would work out well.
And then we have, do you use or need to know pruning percentages for each ACDC stage before starting the training or just at the end?
As mentioned before, you set a parameter for the pruning once, right? So for example, 98%. And then this sparsity is being turned on every time you enter the sparse phase, right? So it's the same sparsity throughout the whole run in the sparse phase. I think this answers the question.
And then final question that we have coming in, could you comment on adapting your technology to Intel's neuromorphic chip architecture?
Once again, Mark, do you have information about that? Very exotic.
I mean, yeah, it's definitely something that we're looking at towards the future, both across a lot of different hardware vendors. It's not anything that is in our short or medium term right now. So it's not on the roadmap quite yet, but it is something that we are trying to strategically position for.
It does sound like like it makes sense. Like there's a lot of research on sparsity, which also kinds of like piggybacks from the like in biology research, because it's also believed that the way our brains work, they employ kind of sparsity, right? So it does sound like those two things go together. Interesting.
Yeah. All right, and that was all of the questions that we had that came in. So I'm just going to add one more plug in here for this, which is that ACDC, as well as all of our other pruning algorithms, we're working on a software called Sparsify that's going to be coming out as a cloud offering and a locally runnable cloud SaaS system that you can use to automatically apply all these pruning techniques and compression techniques to your models through a number of different pathways. So the goal there is to make it as easy as possible to apply the research that we've been doing actively internally at Neural Magic to whatever model you might have. And Sasha sent out a message in the webinar chat. So if anyone is interested in signing up for our early access waitlist for that, definitely do that. We're looking for active testers on that to begin there.
Yeah, I can just reiterate, if you want to be up to date with all our research products and goodies, support us on GitHub, follow us on Twitter. And I would say this is the most important thing if you want to participate actively, and also get help, try to use our stuff, join our community on Slack. We are pretty active there.